This presentation covers part 1 of chapter 5, Writing Classes. This chapter is so important that I've asked you to start reading it and rereading it since the first week. This material is foundational to understanding and being able to develop object-oriented programming solutions. So let's get started. We've talked about classes and objects, and we've used classes in our last programming assignments, but now we want to start writing our own classes. True object-oriented programming is based on defining a set of cooperating objects. That means then that we must define classes that represent those objects with very well-defined characteristics and functionality. So, what exactly is a class? Well, we can think of it as a reusable software component template. We define a class, such as coin.java, that has all the characteristics encapsulated with the operations on the model. So this word encapsulation is an important feature of object-oriented programming and design. What we mean by encapsulation is that we're bundling all of the information about that unit of code in one module, and we call that module the class. You could think of a class as a blueprint for building actual objects. Architects use a blueprint as a guide for building houses. The blueprint class will allow programs to create objects. It gives all the information necessary to create and use objects by defining all of the data variable members that are in the class, as well as all the methods that act on those data members of the class. Another really useful thing about using classes is the idea of classification within a hierarchy. Now, we do this all the time in the real world. And a little bit later this semester, we will be doing it with our classes as well. So for instance, we might create an appliance class and put the general characteristics of appliances within that class description. And then we might have a child class or a derived class for a particular type of appliance, say a stove. With the stove class, we might have to add more details about the appliance, such as is it gas or electric? How many burners does it have? Etc. So we'll be talking more about inheritance and class hierarchies a little bit later this semester, but I didn't want to leave it off this list. A class also could be used for coding abstract data types. And again, this is an important concept in computer science. The ability to describe something in terms of the data and all the actions that work on the data. So the class, when we code it, is a natural extension to this notion of an abstract data type. Finally, when we define them carefully, it provides a very good level of security for objects that we use and create. And we'll talk more about this in the next lecture, but this has to do with the idea of what's called information hiding, and we do that with the visibility modifiers. You've already seen these pop up. Words such as public and private describe who can access the data and when. All right. So the class describes a type of thing. For instance, I could describe class book. I would define class book to have a title, to have an author, to have a number of pages. And then I could create as many objects as I need from that blueprint. These are the actual instances of the book. Java Foundations is a book. Harry Potter and the Goblet of Fire is a book. What the Dog Saw is a book. And every one of them have a title and authors and a number of pages that was described by class book. Another example is a counter. A counter would have a value and an upper limit. We can set the value, we can increment the value. Examples of using class counter and creating objects might be to build an odometer that we use on our car. It has a set value for the number of miles traveled, and it has a limit. And once you reach that limit, you can't go past it. A stopwatch is another example of a counter. So objects have a state. These are defined by the value of its attributes. The attributes in code will be defined as data members. An object also has behaviors that are defined by the methods. And finally, we have to name our objects. So each object has its own unique name within the confines of our program. Figure 5.1 from your textbook. You should take a few minutes to review the sample classes with some of the attributes and operations for those classes. So if we wanted to code class student, we would include a name, an address, a major, and a GPA. Methods we would write would be allowing us to set the address, set the major, and compute the grade point average. Identifying classes and objects. Well, how do we do this? When I read a programming description, how do I formulate a truly object-oriented programming design? One way to start is to read through the narratives and look for the nouns. Generally, classes show up as nouns. Remember, the class is going to represent the concept, and then we can build as many of these actual objects as we need or want in our programs. Here's a narrative for a problem description, and a good way to start is to circle the nouns. That will help us identify classes and objects within the program problem domain. Here's another example. I've already drilled down to a particular class object that we want to code. This is the coin class that was used as an example in the forum. After doing my noun analysis, I've circled coin, which will wind up being our class, face, heads, tails, and user. When I look at this more closely, clearly the face could have a value of heads or tails, and those are the things that are associated with the coin. The user is not part of the coin class. Sometimes it's hard to decide what should be represented as its own individual class. For example, if I have an employee payroll program to write, should I make the employee's address just part of the employee class, or should I have a separate address class? And the more you examine problems in greater detail, the better you'll get at defining and describing your objects and classes. It just takes some practice. If the class is too complex, then it should be decomposed into smaller classes. Remember, when you describe something in a class, it becomes a reusable component. If I have the address buried in the employee, I don't have that as a separate entity that I could reuse in another program. So, when you're trying to decide between should I make it a separate class or not, it's probably best to go ahead and make it a separate class. Now we need to talk about getting something done here. And this is part of assigning responsibilities. Every activity that a program does, it's done in the context of a method. And what we do to identify the methods is to use the verbs. we're looking for action verbs. Now, don't expect to get all of this right the first time around when you're doing design. I like to describe design in two major components. The first one, think about taking a snapshot. You're taking a picture of the entity. You want to describe all of the parts of it in the class first shot design. After we get that worked through, then we'll look at our class more as a moving camera using the class object. How do we need to be able to use it? How do we need to be able to manipulate it? And this too will help us identify missing methods and maybe even missing data variable members for our class. We'll talk more about this over the coming 2 weeks. Here's class coin again, and this time I underlined all the action verbs. So we see the words set and get, flip, and changes. So they're the action of the program. So here's my first cut at class coin. Notice I've included an enumerated type because the only two valid values for the face of the coin would be heads or tails. And what I'm really interested in with this coin is flipping it. I don't care how much it weighs. I don't care what color it is. I just care if it's heads up or tails up. And I want to be able to set it and flip it. Now, generally, we will always provide set and get methods for our class member, such as face. So we see inside coin, and this corresponds to the description that we went through to find the verbs, that we have a get face that will return the value of the face of the coin, whether it be heads or tails, and a set face, where if I needed to, I would be able to set it to either heads or tails. I really want to think about this for a minute. By using the enumerated type face, we have really added a measure of security to our program. What do I mean by that? Well, take a look at the input parameter for set face. The type is face. What are the only two valid values that could be? You got it. Only heads or tails. And so whoever uses a coin, if they don't provide an input of either heads or tails when they attempt to set the face, the code won't even compile. So what that means then is the face value could never be set to an improper value. And this is a hugely important feature of good object-oriented programming. We also made use of the random number generator, well, pseudo-random number generator, that we learned about in Chapter 3. So we're starting to incorporate those new things we're learning right here into our first class coin. We also see the flip, which is going to use that random object rand to arbitrarily set it to heads or tails. And then finally, we have a toString method there, and we'll talk more about that in a few minutes. In your reading, you should have come across the word constructor. A constructor is a special purpose method that's used to instantiate or initialize your object. The constructor has the same name as the class. So it's easy to pick out the constructors. They have to have the same name as the class, and there's no return type, not even void. So let's look at the coin constructor up close. It's pretty simple. We're using this to initially set the face value of the coin to heads. Notice it has the exact same name as the class, but it is a type of method, so we see the parentheses. It doesn't have any input parameter, so those parentheses are empty. And we've preceded it with the keyword public. For now, don't worry too much about that, other than to know that if I use that word public, it means it's available to other parts of the program. One other thing to note here, in order to set the face to heads, I have to include the enumerated type, the dot operator, and then the value. So face on the left side of assignment is a variable of my class. It's an instance variable. And face on the right side, that's capitalized, is the name of that enumerated type. Then the dot operator, and then the value heads. Behind the scenes, Java actually builds enumerated types as classes. And those values that we put between the braces, such as heads and tails, are actually like constant objects that are available to use. More on that later. The toString method allows us to represent our object as a string. And we get to write this so that whatever way makes sense to display our object, we can do so. Now for a coin, really all we're interested in is its face value. So that's all that's going to really be represented by our toString method. But take a minute and think about, what would you want your phone number to look like if you had a phone number object? You would probably want to have parentheses around the area code, then the first 3 numbers, a dash, and the last 4 numbers. So when we write our toString method for a phone number, we would want to include all of that formatting for our phone numbers. And we can do that because for every class we write, we will create our own toString method that applies to that particular class object's representation to the screen. Here's the toString method that I wrote for class coin. Okay, let's take a look at this. Again, it's a public method so that any parts of the program can use it. It returns a string. Initially, I declared a string and I named it cout because I'm sentimental about C++. I initialized it to null. There's an empty string. And then I used that plus equal operator to append face, whatever value is stored in there, whether it's heads or tails. Java will append that to the null string and then return either the value heads or tails as a string from this method. Pretty cool, huh? That covers the coin class, but we still don't have anything to run yet. In order to run the coin class, we have to declare an object. And let's do that and test it out. So for us, we're going to be starting to write reusable software components, simple classes that we test with a driver file. The test coin class is where we'll find the main, and we'll declare a coin object and try out its constructor to build the object, set, flip, and toString methods. So let's take a look at the driver file. We see our public static void main. The first thing we do is give a description of what's going to happen here. I'm going to be testing class coin by creating a coin instance. Then we'll display its value. Then we'll change its value by set method to tails. And we'll display it again to verify that it got updated. And then finally, we'll flip the coin for a random outcome that we will then again display. Okay, so that first set of code there, we have code mypenny equals new coin. This is declaring a coin object. I named it mypenny. And the right-hand side there, we have to do new coin. We're invoking the constructor. And we can tell that we're invoking the constructor because it has the parentheses. So this will instantiate a new coin object, and within this part of the code, its name is mypenny. Then in a system out print line, I show the value of mypenny. And the face value of mypenny was set to heads in the constructor, so we should see that initially the coin is heads. Now look at that closely. I'm using the mypenny object inside the system out print line. That is automatically going to use this toString method that we wrote to display the coin object. Okay. The next line of code, mypenny.setFace to face.tails. This will change the face value inside mypenny to be tails. Then we print that out in a system out print line. After setting to tails, show mypenny. Then we're going to flip the coin. Now I don't know what's going to happen here. It could land heads, it could land tails, because we're using the random number generator for that. Then we print it out again to find out what happened after we flipped the coin. Here's the output from running the program, the description of what we're doing, and then we see the outcome. Initially, coin is heads. After setting to tails, tails. After flipping the coin, tails. You should be able to look at the program code and figure out which line in the program code produced which line in the output. Study it carefully and make sure you understand that. Okay, we're using a modified style called test-driven development. I firmly believe that developers should write test cases early on. Why? Because if you think about testing your code, you'll write it better. You'll have thought through the problem more carefully, and you'll do a better job coding it. Some developers adopt a style called test-driven development. This is where the first thing they do is write their test cases, and then write their code, only enough code to implement those test cases. Well, we're not going to take it to that extreme. We need to become good designers. So we are going to start with our program description, develop our design, formulate a class, and as we're doing that, we'll also be developing our plan for testing it. You will want to be starting to read the notes on test plans and formulating test cases.